Hello and welcome to the final session, the third one on probability for year 12, the stats part of the A-level. So this one's going to be on tree diagrams. The good news is there's not a great deal to say here, and very little extra on top of what you already know for GCSE. So I'm just going to wrap this up with just one quick worked example, then leave it to you to try. Before we do that, as ever, there are some warm-up questions I want you to have a go at. Here they are. I think question one's particularly nice, a bit of thinking for question one. So 1, 2, 3 and 4. For questions 3 and 4, you need to be brushed up with your trig from this year. So pause the video now, and then when you're ready, press play to see the solutions. Okay, so let's have a look now at the answers to the warm-up questions. So warm-up question 1, we've got a bag of counters to make. So we need to make this bag of counters so that the probability of red is less than a quarter, the probability of blue is greater than the probability of being green, and also the probability of being green is half of the sum of blue and red combined. So this is one where there's a few different ways you might be able to do it. I'm just going to show you one way, and I hope you've had a long, good hard think about how to do it. So first thing we need is some counters. So this is a way I thought of doing it. We want blue to be greater than green, and we want the probability of red to be very small. So I'm just going to put one red in and see if we can do it from there. Just one red. And it also says that the probability of green is half the sum of blue and red. So if blue needs to be bigger than green, then we need more blues than we do greens. So what I'm thinking here, we could have 3 blues and just 2 greens. I put 3 blues in because 3 plus 1 gives us 4 red and blues, and half of that is 2, so it hits this rule here. The 2 greens are half of the 4 red and blues. Probability of blue being greater than probability of green, yes, because 3 blues is bigger than 2 greens. And there's only 1 out of 6 which are red, and 1/6 is less than a quarter. So that's one way of doing it, which works absolutely fine. Let's have a look now at question 2. So for question 2, we've got this Venn diagram to fill in. We're told we have 47 students that are asked whether they liked art, biology, or any combination. The results are shown in the table below. So we've got art, biology, if they like both, or like neither. So it says here to complete the Venn diagram. So like I mentioned in the previous session, if you can do, always start with the overlapping section. Always start with the intersections. So the overlapper region is the both section. So if you like art and biology, this is the intersection of art and biology. So this goes in the middle. So that's 11. 30 students liked art. 11 are already ones which also like biology. So 30 minus 11 is 19. So here we put 19 for art. Biology, there's 20 students. So far we have 11 here. 20 minus 11 gives us the other 9. We're now also told that neither is 8, so neither goes on the outside. As a double check, we may as well make sure that these numbers total 47. So 19 plus 11 is 30, plus 9 is 39, plus 8 is 47. So we do indeed have it right. For part B, we need to find the probability of the intersection, so the complement of A and the complement of B. So what I'm going to do here is I'm going to show you the complement of A in a different colour to the complement of B, just so it'll look clearer. So if I do the complement of A, which just means everything that isn't A, in red, and then the same for B in blue, the intersection will be where we can see red and blue together coloured in. So anything that isn't art is all this outside bit here. Everything apart from the art circle. The shading doesn't have to be great, just to be clear enough to make the point. And B dashed, everything apart from this B circle, is going to be everything apart from the biology circle. So we're looking at all of this here. At the bottom as well. And up on the other side of the diagram. So the question now is, where can we see both a mixture of red and blues? Well, in art, there's just blue. In biology, there's just red. In the middle, there's neither. Where there's a mixture of red and blues is just around the outside of the Venn diagram. And so it's the bit which does not have anything to do with either circles. So if I just get rid of what I just did to make it nice and clear again. So what we're after here is this 8. And so 8 is in the region of having nothing to do with A and nothing to do with B. So that's going to be 8 people out of a total of 47. Let's now have a look at question 3. This is what I said you need your trig chops well oiled for. So we need to just rewrite this as that. And so I'm going to start with 3 sine squared x. It's going to copy it out essentially. Minus 2 cos squared x equals 1. We need to remember this identity, that sine squared theta plus cos squared theta equals 1. And from that, our target is something to do only with sine squared, so we want to eliminate anything to do with cos squared. And so we need to write cos squareds in terms of sine squareds. So from this, if we subtract sine squared from both sides, we can see that cos squared theta is going to be the same thing as 1 minus sine squared theta. And so this is going to be our main way into solving this question. So what I'm going to do, I'm going to swap out this cos squared x with 1 minus sine squared x. So the next thing, we have 3, I'll get it in black colour again, black ink. So 3 sine squared x minus 2, then brackets, 1 minus sine squared x equals 1. So now if we expand these brackets, we get 3 sine squared x, minus 2 times 1 is minus 2, minus 2 multiplied by minus sine squared x gives us plus 2 sine squared x, which equals 1, and then we're done pretty much. 3 sine squared plus 2 sine squared gives us 5 sine squared x. And if we add 2 to both sides, this 2 disappears, and 1 plus 2 is 3. And so we've proved which we needed to show. A similar question type for question 4 now. So we need to show that 4 sine x equals 3 tan x can be rewritten in this form. And before we begin, there's another identity we need to remember, and it's the identity that tan of something, in this case tan x, is just sine over cos. So what we can do is we can replace this tan x with sine over cos. And that can be our first step. So this becomes 4 sine x equals 3 lots of sine x over cos x. So this needs to be rearranged so it's all equal to 0. And as you can see here, there's no fractions at all of any type. So on each side, I'm going to multiply through by cos x. So if I do that, I'm going to get 4 sin x cos x on the other side. Equals 3 sin x. If I now subtract 3 sin x from both sides, I get 4 sin x cos x minus 3 sin x equals 0. And now, because I have sin x, which is a factor, a part of both sides, I can factorise out sin x from both parts. So sin x for cos x minus 3 equals 0. And again, that's exactly what we wanted to prove. And so we're done with question 4. Let's now have a look at some questions on tree diagrams, which is going to be the focus of today. So straight into it, let's have a look at a past exam question. So I'm assuming some prior knowledge here from GCSE. So in a factory, we have 3 machines, J, K and L, and these are used to make biscuits. So machine J makes 25% of them, K makes 45%, the rest are made by L. We're then told that all of J, K and L have a probability of breaking the biscuits. So we're told it's known that 2% made by J are broken, 3% of K's are broken, and 5% of L's are broken. First of all, we're asked to draw a tree diagram to illustrate all the possible outcomes and associated probabilities. So one thing we're going to need is the first set of branches, which needs to be 3 branches, 1 for J, 1 for K, 1 for L. And so, like I say, each of these relates to the different machines. So J, K and L. So this first branch is here to represent the probabilities of a random biscuit being made from either J, K and L. So the probability of biscuits made from J is 25%, which is 0.25. 0.45 for K, and for L it's 0.3. And so one event you can think of is which machine's making them. The second event needs to be us considering if a biscuit is broken or not broken. So for each of these machines, J, K and L, we need 2 extra branches coming off them. 1 branch for if the biscuit's broken, another branch for if it's not broken. So we can now fill in these probabilities. So 2% for J, that's going to be 0.02. 3% for K, that's 0.03. And 0.05 for machine L. And to represent broken, I've used B. B dashed just means not broken. So 2% first of all for machine J, we can put in 0.02 at the top. 3% made by machine K, 3% as a decimal is 0.03. So there's a 3% chance here that if it's made by K, it gets broken. And finally, 5% of biscuits made by L are broken, so we're going to put down here 0.05. Now each set of branches always needs to add up to 1. And so each fork needs to add up to 1. So this here, they add up to 1. Here, 0.02 plus something needs to add up to 1. So 1 take 0.02, this needs to be 0.98. For this one, 1 take 0.03, this one is going to be 0.97. And finally, this one down here needs to be 0.95. And finally, 0.95. So what we need to do here is calculate the probabilities of the final bits of the branches. So we do this by multiplying as we move along. And so the probability that J makes a biscuit and it's broken will be 0.25 multiplied by 0.02. So if we do this, 0.25 multiplied by 0.02, that gives us 1 over 200, or as a decimal that would be 0.005. The second one, by the way, if you're wondering how to change your calculator display from doing this to showing a nice decimal number, I'll show you now. If you press Shift, Menu, and scroll down, so it's number 3, number format. Just trying to find it there myself actually. And so we want option 3 for normal. Now weirdly, try pressing option 2. So if you do that and press option 2, it will now come out as a normal looking decimal. So for some reason normal option 2 in many ways makes more sense. So the next one we're going to do 0.25 multiplied by 0.98. Here we get 0.245. Next, 0.45 multiplied by 0.03. We get 0.0135 for that one. Zero 0.45 multiplied by 0.97. Gives us 0.4365. And nearly done. 0.3 times 0.05. It gives us 0.015. And last but not least, we're going to do 0.3 multiplied by 0.95. Which gives us 0.285. So we've done part A now, we've done the tree diagram and every single associated probability. For part B next, we're told that a biscuit is selected at random, and we have to calculate the probability that the biscuit is made by machine J and is not broken. So made by J and not broken. And so we're after this route here. So made by J and isn't broken, it's not broken. So then we go down this route here. So made by J and not broken, that's going to be 0.245. So for B, probability that's made by J, I'll show this with notation, made by J and, so intersection, not broken, equals 0.245. I'm showing here with symbols what this is saying in words. There's no difference apart from just how it looks. They mean one and the same thing. Part C just says to simply calculate the probability that the biscuit is broken. Well, there's 3 different ways of doing this. So one way it could be broken is it's made by J and broken, which is this probability, or the biscuit could have been made by K and is broken, which relates to this probability, or L could have broke it. So the third option is it was made by L and then was broken, which relates finally to this probability. So for part C, the probability the biscuit was broken that's just going to be 0.005 plus 0.0135 plus 0.015. If we add these together on the class whiz, we're done. So 0.005, whoops, plus 0.0135 plus 0.015. That gives us 67 out of 2000, which is fine if you want, or as a decimal we get 0.0335. So roughly a 3% chance overall of biscuits ending up broken on this factory line. That's all I'm going to show you, so I'm going to wrap up there. And I just want you to have a go at these questions if you can do. Page 79 and 80, you'll find exercise 5D. Just try questions 4, question 5, question 6. If you're getting stuck, you may even benefit from rereading your GCSE notes. If you're still stuck, check the answers at the back and maybe work from back to front. If you're still really stuck, you know where to find me. So once again, sincerely thank you for listening. Keep safe, everybody, and you'll see me soon. Bye for now.